Hello and welcome back. Just got some more wire, copper wire, so that I can finish off the old toroid transformer for the great big amplifier power supply. This come from Brocop, who sell wire and various other stuff. With postage it comes to about 13 quid, so it's not too bad. I've already used one of these 500 gram rolls on there, and this should be enough. So basically what I've got on there at the moment is 230 turns. Now then, to calculate how, first off, to calculate what power this transformer is capable of, I weighed it, doubled it, and then I looked up in transformer sales catalogues and all that, looked for one with the same weight and all the rest of it, and then figured it out from there. So looking at similar transformer cores of that weight, I worked out that it's at least 1000 VA or 1 kVA. It could be a bit more. Now then, when using old transformer power cores that you don't have the specifications for, you're winging it. You might really screw up. It's transformer winding is a very complex transformer winding, and designing a transformer is a very complex thing. It's not easy to do. There's a hell of a lot of calculations to do. So here we're winging it basically. Also, hopefully I should be alright, because this transformer core and transformer will be used at less than its capability, and also it will be overwound. So basically I'm using far thicker wire than we need really. This is 18 gauge AWG, average American wire gauge, which should be capable in a transformer like this of at least 10 amps. So if we're working on the assumption that this is about a 100 kVA core, then 10 amps is more than sufficient. Our voltage, mains voltage here is 240 volts times 10, that's 2 kVA, so we're safe there. Because we haven't got any of the information regarding this core's specifications, like I say, we're winging it. So basically I used this formula to get our turns per volt. So you measure the outer diameter, the inner diameter, the height. So you get the outer diameter and take away the inner diameter. Then you times that result by the height, and that will give you, to give you the height. And then you divide that by 2 to give you the core's square area. And then what you do, you get 42, divide that by your core area, and that gives you your turns per volt. In this case it's 1.5 turns, times by our mains voltage, which is 240, that gives us 366.5 turns. Also I'm going to use the lamp limiter to check that that is correct. If that bulb lights up when we connect it to the core, then we know we've not got enough turns. I'm going to put a few extra turns on, probably just to be on the safe side. To calculate the what secondary winding we want, in this case I'm just working on the assumption that this is just going to be for the HT. Working on the worst case scenario with 2000 volts HT, then I divided that by 1.35. 1.35 is a pretty safe assumption for how many volts you're going to get out of it once it's rectified, smoothed and all the rest of it. You can use 1.414, but that's like a good case scenario. So there's going to be some losses. There's going to be all of the power that this primary can provide isn't going to reach the secondary. So if we work on the assumption that 5–10% of the power of the primary winding is going to be lost, then that gives us a fair approximation of the losses that we can expect. Also, there'll be a lot of winding losses, but again, I'm going to use thicker than needed wire for the secondary, so that should cut our losses down. This 1481 volts that we will need to get to 2000 volts is just a estimated sort of figure. What I will do as I wind the secondaries, because there's going to be loads of secondaries, I shall test, once I've got like one secondary to provide 375 volts DC, I shall test that with a load, and then from that I will work out how many other windings I need and what have you. So I'm sort of waffling a bit here. So, and the other thing I'm going to do is at some point when I finish winding the primary, I will go back, count the turns, and then I'm going to take off taps so that it can be run in run with mains of 120 volts and things of that nature. So there's going to be a few taps off there, but for now I'm just going to get the winding on and crack on. Well, I've finished winding. That's all the windings on there, and I've also, let me just make sure you can see that, I've also cut the primary in two. Just got two wires coming out there. That's for 120, 115 volt operation. Alright, just make sure you can see that. So I ended up putting on 370 turns, and now I've just got it upon the variac here. So just make sure I've got this right. So I'm going to run it up on the variac, and this is current, this is why it is an ammeter. So on the left here we've got voltage, on the right here we've got current. No buzzing or horrible noises. 210, and as you can see it remains, this is in amps, so 20 milliamps. No load obviously. This is the sort of mains voltage we usually get here, about 240 volts. So as you can see, the current hasn't changed, and we can go a bit above that, still no change, so that's good. And then if we're connected up to the primary, to the tap, that's a 120 volt tap. As you see, you should see the current goes up. So as you can see, our current is about twice, so that means in actual operation we would have to connect the two halves of the primary in parallel so that we're, everything's cushy. So now it's just a matter of insulating all this, cutting that off, putting the wire on, insulating it, and then putting on the secondaries. Alright, that's the primary, wrapped in one layer of Captain tape and one layer of this, I can't remember, Nomex paper I think it's called. It's just basically brown paper with a sticky back on it. I'm going to put another layer of Captain tape over that, and that should be good, and then I'll test it with the 10 kilovolt insulation tester. Well, here we are another day, sun shining, still bloody cold though, lots of snow still on the ground, nasty horrible wind up your kilt if you go out there. Went out on a motorbike earlier on, oh teeth, my hands when I came back when they started to warm up, you know, chilblains, not nice. Anywho, that's a motorbike by the way. Right, we put the old Nomex paper on there, and then I gave it a coat of this Ultimag 2000/372 varnish, and that's looking good. A little bit of ill fitting, if you can see that. I'll try and hold it up. A little bit of ill fitting in the centre there. The next job is to put an electrostatic shield in there, and apparently I was a bit confused about this because there's different sorts of copper bands that you get in transformers. I'll try and illustrate if I can find the damn transformer. Here it is. So this is the I transformer I wound a while back, and that transformer sits like that. Obviously I can't put it on at the moment. That sits like that, and the two ends are joined. So I was wondering about the two different types of shield. There's this one that goes on the outside of a transformer, and then another one like on this toroid transformer here that goes around the outside, separating the, well, not quite separating, but in between the primary and the secondary. The first one, this one apparently, this one stops any stray magnetic flux coming off the transformer, and as you can see that is joined by soldering, and that basically creates a shorted magnetic turn, generating big currents in this copper band and effectively opposing, I think that's right, the sort of stray magnetic field, you know, that would like interfere in nearby circuits. The second apparently is to interfere with the capacitive coupling between the primary and the secondary. This isn't connected at each end, and what happens is this is grounded to ground or earth. It does two jobs. It creates an electrostatic shield or a Faraday cage, Faraday shield, shunting any high frequency crap that comes off the mains to ground rather than allowing it to go into the secondary. And it also in the case of a fault, if we get a insulation breakdown or short on the secondary, this shunts any current that the primary is trying to shove into the secondary, shunts that to ground, hopefully tripping a either breaking a fuse or tripping a, what the bloody hell do you call, tripping a breaker. Hope that makes sense. So I would like to use some thicker copper, but I haven't got any, so I'm going to use a couple of layers, a couple of, what do you call it, a couple of turns of this. I'm going to stick that to the outside there, and then I'm going to put some more Nomex paper on the outside of that, put some more varnish on it and then surround the whole lot in, what do you call it, tape, captain tape. Right, I hope that makes sense. Right, so I'll crack on with that and we'll be back in a minute. Right, trying to get this so it lies parallel with the top. I love this copper tape, it's great stuff. It loses its sticky quite quickly and it's a little bit flexible. Oops, I'm going off a bit, going off piece there. Oh, nipples. Right, that's on that. And this can go on here now. Just overlapping a little bit, but not in contact with the other. Let's have a bit of an insulation test. Oh, sorry, resistance test. I'm going to test this with my high voltage doodah later. Right, well, I've just connected that up to the mains. No problem at all. That's a couple of turns of Nomex paper. I've done the bottom end. I've just, because it overlapped and it can't go around the curve, I just put a couple of little nips in there. Ow, got cramp in my hand. And now, just going to go round and just make sure it's sealed. Doesn't need it so much on this side. Right, on with some varnish. I don't know what the base of this is, but it's a nightmare to try and keep your brushes clean.